In this section, we are going to derive the capacitance of parallel conductors. So we know that the parallel conductors due to the transmission lines and across which the capacitor exists. And here a section of the transmission line is given. A is one conductor and B is another conductor. They are running parallelly, and the small a is the radius of the conductor A, and small b is the radius of conductor B, and distance from its center is the d. And let us take any point, the P, between the conductor A and conductor B, and it is r distance from the center of conductor A and d minus r distance from the center of conductor B, that we can obtain from the distance which separate conductor A and B. It is d. And the conductor is uniformly charged with a charge density of line charge density of Royal Coulomb per meter, since it is positively charged conductor, and it induces a negative charge on the opposite conductor, that is B. So B become minus Royal Coulomb per meter, which is the line charge density of the conductor B. Now let us see that what is the electric field intensity at point P. It is an arbitrary point anywhere between the conductor A and B. It is r distance from the center of the conductor A and d minus r distance from the center of conductor B, and it would be algebraic sum of electric field intensity due to conductor A and conductor B. The electric field intensity at any point we can describe with the function E is equal to Royal, it is the line charge density, 2 pi epsilon r. Let us take it as the electric field intensity at point P due to the conductor A, EA. And similarly, EB is the electric field intensity at conductor at point P due to the conductor B is Royal 2 pi epsilon. Instead of r, the distance from the center of the conductor to the point P is d minus r. Now the total field electric at point P is EA plus EB. So here we can take out Royal 2 pi epsilon outside. So Royal 2 pi epsilon, and within the bracket 1 by r plus d minus r. Now we need to find the potential difference between the conductors, because from the potential difference we can obtain what is the capacitance of the capacitance due to the parallel conductors. Because capacitance per length, so we know that Q is equal to the CV, so C become Q by V. The V is the potential and Q is the charge. What is the capacitance per unit length? So capacitance per unit length is Q by L by V. So Q by L is the line charge density, which is upon voltage. So this is the C, the capacitance per unit length. So we need to obtain the expression of V, electric potential. So now let us obtain the expression of electric potential between this the parallel conductors. Suppose a unit positive charge is moving from this point to the surface of a conductor, then electric potential is, which is acting against the field, so minus integral of E d r. So from d minus a, so this is this point, d minus a to a. Now we can substitute the expression of E here. So Royal 2 pi epsilon is a constant, so we can take it out. Royal 2 pi epsilon, so minus integration from d minus a to, so this term 1 by r plus 1 by d minus r, integrating with respect to dr. So let us copy this term to the next page here. So minus Royal 2 pi epsilon. So integration of 1 by r with respect to dr is natural log of r. So just substituting the upper and lower limit. So d minus a to a. So integration of 1 by d minus r is minus natural log of d minus r. So the upper and lower limit are d minus a and a. Now take this minus side inside. So this become Royal 2 pi epsilon. So minus of natural log of r. So d minus a to a. So that become, so minus of r a to d minus a. So we can change this minus sign by reversing the upper and lower limit. So this become d minus a to a. So we can know this term. And again plus, so minus of minus plus natural log of d minus r d minus a Royal 2 pi epsilon natural log of d minus a by a plus natural log of d minus r d minus a by d minus a. So this become Royal 2 pi epsilon natural log of d minus a by a plus natural log of d minus a by a. Here natural log of d minus a by a plus natural log of d minus a is 2 natural log of d minus a. So this become Royal 2 pi epsilon 2 natural log of d minus a by a. So here 2 get cancelled. So electric potential become Royal pi epsilon natural log of d minus a by a. Now we are going to connect this with the capacitor. So earlier we have seen what is the connection between capacitance and Royal and V. See here the capacitance per unit length is the line charge density by the potential. So C is Royal by, so let us rearrange, bring V here. So Royal by V, take this on the other side of the equation, natural log of d minus a by a. So Royal by V is the capacitance per unit length. So C we can write as pi epsilon natural log of d minus a by a. If d is much larger than a, then d minus a is approximately d. Then the capacitance become pi epsilon natural log of d by if the medium between the conductors A and B is air, then epsilon become epsilon naught. So this term become epsilon naught. So by the way, this is the capacitance between the two parallel conductors. The pi epsilon naught by natural log of T by A.